For those of you who don't know me, I'm Rajiv Raj. I'm serving as the faculty host for this lecture today. So I welcome you all on behalf of the department to this William H. Mason Memorial Distinguished Lecture. This is the first one. So we are really pleased to have Professor Cummings give this inaugural lecture. And you probably saw from his short bio, he's a professor of aeronautics and also managing director of the Hypersonic Visual Simulation Institute. And he's located at U.S. Air Force Academy in Colorado. And I think he's the perfect speaker to give this inaugural lecture because he has a unique perspective on Professor Mason's lifelong contributions to engineering. And after all, he and Professor Mason co-authored a textbook together on applied computational mathematics and did other things as well. And Professor Cummings is a fellow of AIAA and the Royal Aeronautical Society. And I could cite many more accomplishments, but some of them are listed in the short bio, many of them are not. So, but instead of taking his time here, I'll just ask you to join me in welcoming him to give this lecture. Thank you.
Well, thank you. So it's an honor to be here today to memorialize some of the career of Bill Mason. And I appreciate the invitation to come and speak. I'm glad I could do it in person. Welcome to everyone out there in the world of Zoom and to everyone here in the lecture hall. Thanks for being here today. I am going to go through a number of things about Bill Mason's life and career, but I'm going to concentrate on the time he spent interacting with and at the U.S. Air Force Academy. I realized there's going to be other people giving lectures about Bill Mason's, so I don't want to take all the material away and leave them something to talk about. So I'm going to hopefully go to the next slide. Let's see what happens here. Oh, it's hooked up to this. That works. Okay, there we go. Give an overview of Bill's career, but in his own words. And the way I can do that is that for the book, one of the things we included was biographies of people who were practitioners of computational aerodynamics. And Bill wrote his own bio, so I can use that today. And then to talk about the time he spent at the Air Force Academy, but also tell you a little bit about the Air Force Academy because it's a little bit different than a lot of universities. Also, he conducted CFD research when he was at the Academy. And of course, we were working on writing the textbook. And I thought a good quote to start with would be one that was given by Lee Nicolai, who's a aircraft design god from Lockheed Martin, Skunk Works, who in a memorial session at the NAIAA meeting said, "Yeah, I knew Bill, I didn't like him. He knew more about aircraft design than I did." And that was tongue in cheek. They were lifelong friends. So I thought the first thing I'd start with is a quote from a very famous aerodynamicist, A.M.O. Smith. People called him AMO. His initials were AMO and they just called him AMO. He was the chief of aerodynamics engineering research at Douglas Aircraft and later McDonnell Douglas. And his career went all the way back to the 1930s when Donald Douglas Jr. was taking courses in aerodynamics at Caltech and would come to A.M.O. Smith for help with his homework. And then later in his career, Donald Douglas was giving him a 25-year pin and asking what he was working on. And he said, "I'm still trying to learn about aerodynamics." And for those of you who have maybe taken a course in aerodynamics or even studied it deeply, I know for myself, it's something you never stop learning about. It never is decided. It is never complete. Turbulence has something to do with that, but certainly Bill agrees with this. a great deal. So he was someone who spent his entire life trying to understand aerodynamics as well. So in Bill's own words, the grew up in Winchester, Virginia, that's my words, but then the smaller bullets are literally things he wrote about himself, that he, as he was growing up, built and flew model airplanes and competed in control Maryland. And he began to realize while he was doing that, the importance of a few small details that students usually forget about. And that is, you have to be able to start the engine and you have to be able to build a good structure. Otherwise, the flight's really. And then after that, then you can try to make things better with the stability control and aerodynamics. When he talked about his time at, as a bachelor's student at Virginia Tech, I thought it was interesting. Everything he wrote was about going to do internships at, and then later at Edwards Air Force Base. So to him, it was those applications of his knowledge out in the real world that really brought it home. And he really enjoyed learning from and growing from as he went through. In fact, he specifically talks in his bio about the motivation that walking past the assembly line had on him every day to see the end product being built and realizing how he could participate in that process. And he stayed at Virginia Tech from 71 to 75 for his master's and PhD. He did them just boom, 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 all straight through. His master's was studying trailing vortices, and his PhD was computational predictions of transonic shock boundary layer interactions. There's a picture that I think is even on the website here. I put quotes around collecting, Bill collecting data, because if you look at the picture, he's actually not collecting any data. He's standing there talking, and other people are collecting data. So maybe that should be Bill managing the collection of data. I'm not sure, but he didn't really care, I don't think, about where to his pursuit of aerodynamics and design. It could be a wind tunnel, it could be a code, it could be some just common or everyday knowledge. That didn't matter to him. It was all about being able to understand something and use that. After he got his PhD, he went to work for Grumman Aerospace. So from 74 to 89, he was there. The first year in the dynamic aeroelasticity, and then the rest of his time there in the aerodynamics section, working on a variety of tactical aircraft, including the X-29. If you don't know or haven't heard Bill's story about working on the X-29, maybe somebody else someday will have that be their talk in memory of Bill. He's the one that predicted the X-29 would be 35% unstable. And then of course, everyone laughed and said, well, that plane will never fly. And then that's when they proved that control systems could fly a very unstable aircraft. And then at the end of his career, he was working on various fighter design projects. So in 1989, Bill decided to come back to Virginia Tech as a faculty member. And he was here until he retired in 2010, and then continued as a professor emeritus. He still came to campus all the time. In fact, he would tell me on the phone, I didn't know I'd be so busy in retirement. I still have committees I'm on, students I'm working with, classes I'm teaching, and he was enjoying himself. He loved teaching design. He loved working with design teams. And he also became part of a group that was applying to design on things like the strut-braced wing. So as I said, he retired and became emeritus in 2010. And in his bio, after that, saying, I retired in 2010, and I continue to try to learn aerodynamics. And then during 2007, 2008, he came to the Air Force Academy as a distinguished visiting professor. And there's a reason for that, and I'll explain it in a minute. We have a program where we bring faculty from around the country to the Air Force Academy for a year or sometimes longer, and they become part of our department, teach some courses, give feedback on relevance, on approach from their experience, and also participate in all of the activities, curriculum, et cetera, in the department. So when I was making these slides, thinking, well, out of all those things he just described that he did, I can't talk about all of them. So I'm really going to concentrate on his time working with and being at the Air Force Academy. If you haven't seen this picture, this is also from the website. There's probably no place he was happier than being surrounded by airplanes, pictures, models, real airplanes. And so that's Bill in his office here at Virginia Tech. So my interactions with him, I first met Bill in the 1980s at a Pan Air short course at NASA Ames. Pan Air is a panel method, but it was a panel method developed by NASA and Boeing for full commercial aircraft, full-size commercial aircraft. And so it was, for its time, a state-of-the-art code for predicting commercial aircraft aerodynamics. So we were at that together, and I put 1980s because I thought it might sound better if you thought it was 1989 instead of 1981 or whenever it actually was. It was a while ago. And Bill and I interacted on the NASA Aeronautics Multidisciplinary Design and Analysis Fellowship Program. That's a long title, AMDAF, from about 93 to 99. 5 universities were chosen to have this program going on by NASA, and Virginia Tech and Cal Poly were 2 of those, and I was at Cal Poly at the time as a professor. And then our interaction kind of increased exponentially when we started talking to each other about the computational aerodynamics textbook. There's also a lot of parallelism in our careers. So Bill started at Virginia Tech in the late 60s. He went straight through bachelor's, master's, PhD, and then went to Grumman, and then came back to his alma mater as a professor. And my career path was similar. I started at Cal Poly, but I let Hughes Aircraft Company pay for me to go to graduate school at USC. And then I returned to my alma mater, Cal Poly, for 18 years before moving to the Air Force Academy in 2001. So we had similar backgrounds. There's not a lot of faculty these days who have spent a significant amount of time in the aerospace industry. And I think, especially if you've ever sat in a classroom with Bill or talked to him, you can tell that when you interact with him. So I thought I'd tell you a little bit about the Air Force Academy. So James, this is you don't need to listen to this part. You know this pretty well. In case you don't know, there's this little school near Colorado Springs. It used to be near Colorado Springs. It's not anymore. It's surrounded by Colorado Springs, called the U.S. Air Force Academy. The Academy was built in the 1950s. Most of the famous buildings are from that time period. And right now, if you were there, Cadet Chapel would look like a white rectangular box because it's having its first major refurbishment in over 50 years. So it's not very exciting to look at the moment. Just some facts about the Academy. So it's 66, now 67 years old. We only have about 4,000 students at one time, and they're all undergraduates. There are no graduate students at the Air Force Academy. There's 32 academic majors, and I hesitated to put this on there, and almost the same number of Division I athletics teams. I don't know what that means, but there's a lot of sports going on and other things. There have been lots of cadets. Many of the cadets come to the Academy wanting to excel in different aspects of an Air Force career. They want to be astronauts. They want to be Rhodes Scholars, Marshall Scholars, and we have the joy of kind of helping them along that path. In spite of the fact that we're an undergraduate-only university, we have a significant amount of research going on in the Academy that has multiple purposes. Certainly, we intend to and do in the aeronautics department include the cadets in our research programs. But we also support the Air Force, and it's also important for faculty development that goes on. But then people ask the question, well, how does that happen? If you only have undergraduates, how do you research? And this is the answer. We are part of AFRL's outreach to faculty and also AFOSR's outreach through the NRC postdoc program, the AFRL Summer Faculty Fellowship Program, Windows on Science, which brings people from other countries to the US to spend time at universities and other locations. The DoD Engineering Science Exchange Program, which brings government workers from other countries to the US to work on these projects and programs. And then we have the Visiting Professor Program, which is what Bill participated in. And then we send cadets out every summer to do research at other locations, including universities. We have visiting graduate students, visiting professors, postdocs, research staff, and some pretty good research facilities of our own doing research. In fact, we have relations with UC Boulder because the Aero program at UC Boulder has, how many wind tunnels do you think? 0. So they work with us when they need a wind tunnel. They don't have their own. The aeronautics lab at the academy is about 50,000 square feet. So other than office space, which is in the academic building, most of everything that happens in the department is in this lab. There's a subsonic wind tunnel, 3 foot by 3 foot, up to Mach 0.6, 2 low speed wind tunnels. There's a trisonic wind tunnel, goes up to about Mach 4.5, the Mach 6 Ludwig tube, engine test cells, so turbofans and jets and all kinds of rockets, combustion shock tube, and many other shops and facilities in that lab. In addition, we have a UAS airstrip on the base. The base is massive. The area where the cadets are and the educational aspect is quite small, but the base is over 5,000 acres and includes the mountains you see behind the academy. This is the newest of our wind tunnels, the Mach 6 Ludwig tube. It is a tunnel that was provided through the DURP program from the DoD, and the Mach number is obvious, it's Mach 6, but Reynolds numbers, unit Reynolds numbers between about 5 and 30 per million per meter, and a variety of data acquisition systems for the tunnel. Also at the academy, it was mentioned that I'm the director of the DoD High Performance Computing Modernization Programs, Hypersonic Vehicle Simulation Institute, HPSI. That institute is not just an Air Force Academy institute. It is an institute that uses research around the country for improving the simulation of hypersonic vehicles. So let's get into Bill coming to the academy. Like the visiting professor program, typically people come for a year, an academic year, chosen maybe a year before that, so that all the logistics can be worked out. And Bill came in 2007, 2008. He moved to Colorado Springs in July of 2007, because at the academy, all new faculty have to go through teacher orientation and teacher training. Some of you might like that. I don't know. All of your faculty would do that. I know it's great for people like James when he came to the academy as a young officer to get some experience in the classroom with the rest of us sitting in the desks acting like cadets and giving him a hard time. So we try to do that for everybody. While he was at the academy, he lived in an apartment and he just loved this. That was a few feet away from Kelly Johnson Boulevard. Kelly Johnson was the famous air designer at the Skunk Works, and Bill didn't know it before he came, but the apartment he had chosen and rented was right off that street. He taught aircraft design and computational aerodynamics at the academy. If you know that's what he did here, that makes sense. And he was very interactive with the things going on there, gave lots of feedback and input. He also participated in CFD research with me and some other people at the academy. And then of course, the reason we brought him to the academy was because of the textbook in applied computational aerodynamics. And then he spent the year and then moved back here to Blacksburg. Snapshots of how things might be a little different at the academy than they are, as we call them, civilian universities. I know when I first went to the academy, I didn't like that phrase, but that's what we say, civilian universities. So arriving on campus on the left, that's kids who are about 2 to 3 weeks past graduating school, having to show up at the academy by the end of June because they have to go through basic training for the summer, get yelled at and marked. So it's a little bit different when they move in. They only have one suitcase, which is basically a book bag, and that's all they can come with. They get to bring more stuff later, but not when they first arrive. Here's casual time differences between civilian universities and the academy. There's not a lot of casual time at the academy. So between their regular education, their military training, and their athletic training, they're pretty busy. Extracurricular activities at the academy are usually really intense, like being on the skydiving team or the gliding team or the cross-country teams and things like that. Like I said, lots of athletics at the academy. I think it was about a quarter of all the cadets are in NCAA athletics teams. So they're busy too. And then special occasions can be a little bit different. Marching onto the field for graduation is kind of special at the Air Force Academy. And then having the Thunderbirds fly over afterwards is special too. And then some things are the same, even at the academy, the football games and the things that go along with university life. But the things I wanted to talk about that are different, I'm pretty sure, are the things that, the reason why visiting professors have to go through that teacher training in July before the university year starts is because they have to understand and enforce all of the military details. They're not in the military. If the instructor is not in the military, they still have to enforce these. Such things as, how does class start, James?
We're ready to learn.
At attention. The class comes to attention, just like that, and one of them reports in that they're ready to learn. I kind of like that. I think that's kind of fun. They all have to be in uniform all the time. Uniforms vary, there's different kinds of uniforms, but they have to be in uniform. And I've had people visiting with me who it drove them nuts. The cadets constantly refer to them as sir or ma'am, but you cannot stop them from doing that. It's been drilled into their heads. Attendance for every class, they're supposed to be at every class. And if they're not, they're supposed to have an excused reason for not being there before class starts. In the classroom, they can't sleep, chew gum, eat, drink other than water from an approved water bottle, daydream. They can't look out the windows. One reason is there are no windows in the classrooms at the academy, and use cell phones. You know, essentially they're just supposed to listen and take notes. This is literally from the classroom standards for this academic year. So they're supposed to stand at attention when the instructors enter the room. That's nice too. Attendance is mandatory. They have to be there on time, prepared, and they have to have a legal copy of all the class materials, including the textbook. No excuse. You have to have it. In spite of all that though, cadets love to get away with the smallest little things that they think that's just the greatest that ever happened, that they pulled the wool over your eyes and took a sip out of a non-approved water bottle. And so Bill, for example, had to learn all of these rules and regulations and try to enforce them. So that's why he had to come early. A lot of people who visit, or at least some of them, don't like that. Don't like it at all. But that is part of the job being at the academy. So it does take a period of transition. I remember the first day as a visiting professor in my first class, before class started, a cadet came in and said, "Is it okay if I go get some breakfast and bring it back to class?" So it was like the first test of whether I was listening to all the rules and regulations happened the first minute I met a cadet. And I already talked about orientation and teacher training. Teacher training are what we call practice teaches, can be quite fun. These sit and not only ask you questions about whatever the subject is, aerodynamics or flow separation or whatever it might be, but also see if you're paying attention to the fact that they had their cell phone out or came in late or whatever it might be. So while Bill was there, he was working on CFD research. I had a postdoc that was working on this program, trying to do predictions of a vehicle called the Modular Transonic Vortex Interaction Configuration, TVI, that was from NASA Langley. It had been created to have a vehicle with very accessible wind tunnel data that was open for people to use, and to then compare with computational simulations to see if you could predict the stability and control characteristics of this vehicle using state-of-the-art CFD codes at the time. The answer was, for the case that we chose in this program called COMSEC, which is Computational Stability and Control, no one had ever been able to predict what I'm about to show you. Nobody. So we chose that as our project. It was very difficult, very challenging. And this just shows a little bit of that. Got roll moment on the left, yaw moment on the right versus side slip beta. It's absolute value because they took positive and negative side slip data. And hopefully the first thing you notice is that incredible nonlinearity that happens between 1 and 2 degrees of beta. Both the roll moment changes sign from negative to positive as you go from 1 to 2 degrees. And the yaw moment value goes from quite a relatively high value to 0. And this is what people had not been able to predict with the current CFD codes at the time. When we started doing the simulations, it was quite straightforward to get some of these values at the higher side slip angles, but it was very challenging to try to get the values between 1 and 2 degrees. The configuration was at 30 degrees angle of attack, Mach 0.4, and it was the tailless configuration, which is why if you put the tail on, this kind of becomes insignificant, but we wanted to try this case. And Bill worked, I have to say, incredibly well with the postdoc, very supportive. The postdoc was constantly apologizing that he wasn't getting results. And Bill would remind him, there are years of people before you who have tried to do this case and haven't been able to do it. So don't apologize. But eventually we figured out that there was a great deal of hysteresis going on and then tracked down why. This is on the left is the roll moment as a function of time, where we start the simulation at 1 degree of side slip, and then we put in free stream conditions at 2 degrees. So it's a time history of going from 1 to 2. And you see, you start off at that negative roll moment, and then go to a positive roll moment and become quite unsteady. Now, this is going to be, we'll see if this movie works. And it doesn't look like it's going to. There it goes. So you start off at 1 degree, and the vortices coming off the chine forebody and the delta wing are quite symmetric and interact with each other. And then about now, the right-hand wing vortices break down and the left-hand wing vortices don't. And that's where that roll moment change comes from. To get that to work, with including the hysteresis, you had to start from the right condition. Otherwise, you wouldn't see it. You would never see it. And you would never see it if you didn't use Taschetti simulation. If you just use URANs, you wouldn't get the answer. So it took almost the entire time Bill was there. That was kind of an interesting project to work on together. And then, like I said, the reason we were there was the textbook. We had started a computational aerodynamics course at the Academy in 2002, 2003, required for all aeronautical engineering students. And very quickly after we started the course, the cadets were quite vocal about what they didn't like. And one of the things they didn't like was there was no textbook. And we kept telling them, yeah, there's no textbook. It's not just that we don't like the textbook, there's no textbook. And so notes and putting them into PDF files so we could share them with the cadets, and then started thinking, oh, do we want to write a textbook out of this or not? And then as we went through that process, someone said, you know, Bill Mason at Virginia Tech has similar set of notes from his course. Maybe you should talk to him and interact and maybe merge your material and write a textbook. So that's what started the discussions that led to Bill coming to the Air Force Academy in 2007. One thing we had to constantly remind ourselves about was we were writing this for undergraduates. There's lots of CFD books for graduate students. And if you think about it, they're written to help you code a program for CFD by telling you all the details of the methods and how to analyze the results. But they're not written to be a good user of a code that already exists, what we call an intelligent user. And we had to remind ourselves about the textbook. You can imagine this. The faculty member usually wants to tell you everything they know. And everything they know may be twice as much as you need to know, and 10 times over your head. So we really had to think about that as we were writing the book. Here's just some of the chapters. So these are merged between the ones that we had written and the ones that Bill had written. So for example, the chapter on linear theory, so panel methods, vortex lattice methods, Bill had used those his entire career, and he really wanted that to be in the book. And that's one of the reasons we didn't call it computational fluid dynamics. We called it computational aerodynamics, is because it included various fidelities of simulation. The second chapter there on computers, codes, and engineering was to introduce the concept of learning how to use a code and becoming a good user of it, because you were familiar not only with how to run the code, but what was inside of it and the various aspects of that. And then some things that are pretty normal. So CFD methods, et cetera. Now, one of the things that we wanted to do was use some programs in the book. So we wanted to ensure that there were programs that students could use to do the projects in the book. But we also added some other features in the book about to try to make this a little more accessible for undergraduates. So there were concept boxes throughout the book, as well as flow visualization boxes. So they were learning about flow. If you're going to do CFD, when I learned CFD back in the 80s, I was told you have to know a lot about fluid dynamics, about numerical methods, and about computers. You had to know all three of those things to be a good practitioner of CFD. So we wanted to add those things to the course. And then, as I mentioned, we had profiles, both very experienced CFD practitioners, but also young, new, energetic people at companies like Airbus and Boeing who were learning CFD in their careers. And then also at the end of each chapter, we had a section of best practices, and Bill was instrumental in helping to add that information. So here's just a regular one of the concept boxes. This is trying to show the difference between something that's linear and nonlinear, because we say that all the time, but what does it mean? We also had these flow visualization boxes, and they went along with the software the students could use to actually recreate the same visualizations on their laptop, and then just see what the different solutions looked like and what was happening as the flow went around the airfoil. This is one of the profiles of people who did computational aerodynamics. This is Earl Merman from MIT. There were people from all over the world included, both young and old. And then this is an example of the summary of best practices. I like on the number 4 here, I said, one of the biggest sources of error in computational aerodynamics is you. Because it's true. When you're just learning to use a code, it's really easy just to put things in and push go and get really bad answers. So we wanted to make sure that that came across. Now, writing a textbook with Bill wasn't always easy. Bill, if you ever were around him, had very high standards. That's nothing wrong with that. Demanding, but he was also very gentle and supportive in wanting to things. So one of the chapters that he was the primary author on was the panel methods chapter. And when he sent me the first version of the panel methods chapter, it kind of looked like that. And I said, Bill, is that necessary? Do undergraduates need to see all that to understand how to use a vortex lattice code? And this is constantly going back to our model of educating intelligent users. So we would have philosophical discussions all day long about how much do they need to know versus how much do they just need to understand, and those kinds of details. Questions all the time. Then though, the practical side of Bill would come out. So using like a vortex lattice code to do a prediction of a configuration, having experimental data, flight test data to compare it with, trying to understand why, when, how it worked, and when it didn't work. Those were things he was fantastic at, and we made sure that all of those things were in the book. The problem was the programs. If you know your department's website has Bill's web pages still on it. And the reason that's true is because people from all over the world still use them. And one of the pages that's on there, I took a snapshot of it here, is this page full of software for aerodynamics and aircraft design. And Bill wanted to use those programs in the book. And that's when we had our biggest conversation. And I'll show you why in a minute. This is just half of that web page, half of the programs that he has there available for things like airfoils, wings, full configurations, aircraft design, cost estimation, you name it, it's there. The problem was those programs were all written in very old Fortran from the 1980s and still were written added inputs that had been written for punched cards on mainframe computers. And Bill never would change that. It's the program. I didn't write the program, somebody wrote the program. That's what it's gonna be. So what did that mean? That meant there were generations of Virginia Tech students who, when they asked Bill Mason for a program that could do vortex, he gave them a program and said, and by the way, your formats have to follow this procedure exactly or it won't work. And generations of students complained about that. Why? Why do I have to follow that prescription to get the program to work? They didn't understand. What they didn't understand was the program had been written with these punch cards in mind. These are a Fortran punch card that you would write a program on, and it had different columns that were for different things. The first column was for a done with it. It was just a comment. You put something in the first column, and statement numbers, continuation, and then the main program was in columns 7 through 72. How come I remember that? That's just, oh, that's disgusting. And each card was one line of the code. So if you had a 10,000 line code, you had 10,000 plus a few at the front to tell the computer how to run it. Those cards had to be punched with an IBM card punch machine. I spent more hours of my life sitting at a contraption like that. And then you had to make sure you didn't drop the deck of cards because they had to be in the right order. And if you dropped them, they'd be out of order. So people used to put them in boxes. In fact, here's a picture from the National Archives in the 1960s of programs that were deemed to be essential for the nation. And they were stored. I mean, it reminds me of Raiders of the Lost Ark, right? Just this warehouse with an infinite number of punched cards in it. So one of the things we did to improve that is come up with Bill's Programs version 2.0. We took royalties from the book and he chose the 6 most important programs that he had on his website. And we hired somebody to make GUI programs that were available for anybody who wanted to use them. So this is induced drag program on the left, the airfoil program on the right that included different solution methods. So you could actually do some calculations and see how long it would take to converge to the right solution. And we released those. They're on the book website and they're free for anybody to use. And so we were literally doing that up to the week that he passed away in 2019. He wanted to get those programs out in a more useful kind of approach. Another problem we had was at one point, Cambridge University Press said, we need a picture of each of the authors. Bill, send me a picture. So he sent me this. It was taken, I think, by one of his family members at a restaurant here in Blacksburg. And I said, Bill, when did you start growing long hair? He goes, I don't have long hair. Well, it looks like you do in the picture because the woman at the table behind you is sitting almost exactly behind your head, wearing a shirt with almost the exact same color, and it looks like it's you. I can't put that in the book. Luckily, the department took some faculty photos very soon after that, and this is what was included in the book, which was a little bit better. That was fun. And then in the year 2015, the book came out. Cambridge University Press published this book, Applied Computational Aerodynamics. 4 co-authors, Bill's on there. 2007, 2008. The book came out in 2015. So most of that time period between 2007 and 2015, making sure that things were pedagogically sound, incorporating projects in the programs, and making sure it all made sense. I know for a fact that Bill was incredibly proud when the book came out. He had been wanting to publish either his configuration aerodynamics notes or his computational aerodynamics notes as a book for many, many years. And he sent me a picture of the first copy of the book that he received in his office here 30 seconds after he got it. He was very excited. Cambridge Press has asked us to write a 2nd edition of the book, and we're going to dedicate that 2nd edition to Bill for all of the things to computational aerodynamics and all of the things he did in his career, especially for aircraft design. One last thing is AIAA had a memorial session at the AIAA Aviation meeting in 2019. There was a room full of people and they've been asked to come prepared to share stories. First, when did you first meet Bill? Colleagues, people that work with him, stories from students, that was probably the best part, and stories from people who he mentored. And then also what was called his quips and quibbles bothered him that students did on a regular basis. And he would remind them about that all the time, very gently. People shared some of those situations. It was a lot of fun. that's actually where Lee Nicolai said, I knew Bill and I don't like him. And so that was a really nice way for us all to sit around and talk about Bill and his career. So just in summary, it's pretty rare these days, if you go around the country and look at aircraft design courses at universities, to find somebody with the combination of academic capability and very practical experience teaching aircraft design and doing aircraft design research. And he was really a pioneer in applying some of those methods, especially for design from the CFD world. He ensured that the codes he used had been fully checked out and had been validated. He insisted that his students do that as well. And it was an important part of what he had done. And like I said, he was thrilled when the book came out with a lot of his life experience inside of it. And I would say, I just wanted to finish with that thing I started with, A.M.O. Smith's quote, "I'm still trying to learn about aerodynamics." That was Bill. Every day he'd learn something new. He might email about it or call me about it or talk to other people. He was always excited about learning something new about aerodynamics and aircraft design. So with that, I will stop and see if anybody has any questions. Any questions? Are there any from the Zoom call?
I'm asking now.
Okay. Yeah.
So what's the plan for the second edition textbook?
So one of the things we want to do is have free Navier-Stokes solver available to the students using the book, and that the projects incorporate the use of that solver so that it's just seamlessly incorporated into the book. To this point, that hasn't been easy to do. Most Navier-Stokes solvers are commercial or somebody's private research code that no student from another university would want to touch. And so we want to have that ability. So not just the programs like I talked about, maybe Vortex Lattice programs, but a Navier-Stokes solver and have that threaded through the book. That's the biggest thing, I think. Good question. Yeah.
Yeah, this is not really a question. I'm Stefano Brizzolari. I'm a faculty here in the Aerospace and Ocean Engineering Department. I come from the ocean engineering side. I must tell that it's a testimonial, if you like. Why I learned about, I became passionate about aerodynamics and in particular vortex lattice code and panel methods was thanks to the website of Bill Mason.
Right.
I was still in Italy at that time. I was a student. I was learning naval architecture, ocean waves, motion of ships in waves, nothing about lifting surfaces or lift and induced drag. But the reason why I became passionate on aerodynamics things was because of Bill Mason website and his notes. So for me, it has been a very precious contribution to the work.
I hear, I mean, thank you for sharing that. I've heard that from people all over the world, that wherever you go, people know about that website. And what were you saying? It's one of the most used websites on the campus. I completely believe that. His course, if you didn't know, in configuration aerodynamics is pretty unique.
Yeah.
Very few people in the world teach that course. Very few people in the world could teach that course.
I agree with you. So the combination between his practical experience as a designer in the industry and his very solid theoretical background made him
Blessed to have him here. Last chance for a question.
Anyone here took any classes with Professor Mason with that? You did? Okay.
There's a few left.
Yeah, he kept teaching, as you know,
Yeah.
at least one course every year.
Yeah, he kept complaining about being so busy after he retired.
Yeah.
Work every day. I don't know what happened, but he loved every minute of it. Okay, well, I don't want to take up too much more of your time, so thank you for being here. Oh.
We've been honored to have Professor Russ Cummings be our inaugural speaker for the Professor William Mason Memorial Lecture. I can think of no one who would have been a better choice for us to have for the first lecture to honor Bill Mason. It really struck me as I listened to you how much you were birds of a feather. So some of his endearing qualities come across listening to you as well. Your intellectual curiosity, your interest in learning and students. And it just reminded me so much of Bill Mason to have you here. So I can't thank you enough for that. I'll tell one little story that I shared with you about how Bill was.
Yeah.
That I think his office was right around the corner from a room where I often was assigned to teach. And every so often, Bill would walk by on the way to his stop, and he'd stand there and listen. And then later that day or next day, he'd come by my office and say, I heard you mention this in your class, and I wanted to let you know that this is what happened on this aircraft. So and that was his nature. He was so generous, and you are as well. So we would like to have you have a small gift from us, a little swag to take back with you that we hope that you'll wear proudly. One of our AOE shirts.
Wonderful. Thank you very much.
With our department on it, and a cup to drink some of that. This is a legal cup you may use in the classroom.
Water.
Yeah, that's officially sanctioned for water in the classroom.
Thank you very
So,
much.
thank you very much.